Hello everyone. My name is Anisha. I am from IIT Delhi. I will be your maths faculty for class 12 mathematics NCERT. If you have to score good in mathematics, then you are at right place. Today we will learn about the chapter continuity and differentiability, which is a chapter 5 of NCERT. The topic which will be covered today are this will be an introductory video, then you in which we will cover the following topics that are continuity, algebra of a continuous function, differentiability, derivative of a composite functions, derivatives of an implicit function, derivative of inverse trigonometric function, derivative of exponential and logarithmic functions, which is a star topic that is very important. Then logarithmic differentiation, then derivative of function in parametric term. Let's begin this chapter with topic by topic. First of all, continuity. Let's begin about with continuity at a point x equals to c. Let's say x equals to c. Let f be our real valued function. It is our real valued function. And let's say d be its domain. Then we say our function f is continuous. I will write it in short form, that is CONTI for the continuity. Continuous at say x equals to c, where our c belongs to our domain, when, or we say if the limit of the function at c, that is limit x tends to c, f of x will be equal to our function value, that is f equals to c. So what is our definition for the continuity at a point? The function is said to be continuous at a point if the function value exists. That means this should exist, okay, right? This should exist. What do you mean by exist? That means the value should be finite. Okay, so what we are saying, our function f is said to be continuous at a point c in the domain if its limit value and the function value are same and these values are finite. Okay, now let's take an example. For example, take the function f of x equals to x. Then see, take at x equals to 1. Then we see that the limit x tends to 1 of f of x, which is nothing but limit of x tends to 1 of x. We know that this limit is nothing but 1, and our function value, that is f of 1, is nothing but 1. So what we see, that the limit value and the function value are same. So what we get from here, that our function f is continuous at x equals to 1. Okay, now see, so if so another definition, that if our function f is not continuous, say at x equals to a, then we say, or we call it as, we call it discontinuous at x equals to a. So there are two possibilities. So when will be our function is discontinuous? Discontinuous, say at x equals to a. What are the possibilities? First of all, there are two possibilities. Case 1, when our limit exists, that is limit x equals to a, f of x, it exists and function value also exists. That means function is defined at a. And already we are taking our a from the domain, so it will always exist. But suppose it exists and it also exists, but the value is not same. That means the limit value x tends to a, f of x is not equals to f of a. This is the one possibility when we say that our function is not continuous at a, or we say discontinuous at a. Then another possibility is that the limit does not exist. That means that the limit x tends to a, f of x does not exist. And we know that limit does not exist when our left hand limit is not equals to our right hand limit. If limit does not exist, then it's not point to match it with the function value. So there are the two possibilities that the function is not as function will be discontinuous. First one, that the limit exists but not equal to the function value. Then the second one is the limit itself does not exist. Now see, this we talk. So okay, what we talk here is the discontinuity of a function at a point. Now suppose if I will tell you some example, take a example as function takes the value 1. This is 1, right? This is 1. This is our x-axis. This is our y-axis. It take value 1 in whole except as x equals to 0. And at x equals to 0, it take the value 2. That is, here it is. This point is 0, 2. So our function is defined as, our f of x is defined as, it takes the value 1 for x not equals to 0, and it's take the value, okay, it's take the value Let's take the value 1 for not equals to 0. Okay, I have like erased the wrong right part. Okay, so it takes the value 2 for x equals to 0. As we can see, our right hand limit at x equals to 0 is 1. And sorry, left hand limit is 1, and our right hand limit at x equals to 0, which is also 1. But our limiting value, that is limit x tends to 1, f of x is 1, but which is not equals to f of, like we are taking at 0, not at 1. Limit x tends to 0, f of x is 1, but it is not equals to f of 0 because f of 0 is 2. So from here what we conclude that our function f is discontinuous at x equals to 0. But also if see, in this type of like discontinuity and continuity, there is always a type of question, that is question find the points where function is discontinuous. This is a standard question that always like come in your exams. So here we can see that the function is continuous everywhere. For example, if I take my x for less than 1, take so take our take our point to check for x less than 1 the function is continuous. Take any point, say c, in minus infinity to, sorry, it's 0, minus infinity to 0, open 0, then we know that our limit of x tends to c of f of x, this will take the value 1, and our f of c value is also 1. So here what we get, the f is continuous at x equals to c. Similarly, we can easily find that whenever my c comes from this side, that means if my c comes from 0 to infinity, then also f is continuous. So what we get in this graph, that means in this example, in this our star example, our f is discontinuous only at x equals to 0. So how many number of discontinuous points are there? Only 1. So there, in this question, this type of question always comes in the exam, that we have to find how many points are there where the function is discontinuous. So here it is 1. So like what we have to find, we have to just check whether the function is continuous or not. We have to find the points where the function is discontinuous. Now let's move ahead. Okay. Now we will define our continuous function. What is continuous function? Suppose our f is a function from, say, is a real valued function, x is a subset of R to R. It is a real valued function. Then f is said to be continuous function if our f is continuous if our f is continuous at all points in its domain. Okay, this is the just normal definition. The function is said to be continuous when it is continuous at all its points. Then we say that the function is continuous. For example, let's take an example that suppose if my function f is defined from closed interval a b to r. When we say that the function is continuous, so for that, for f to be continuous function, f must be continuous at all points in close a to b. So now if I have a point say x or say c in open interval a comma b, then it's fine, easy to check whether the function is continuous or not. Its easy definition is limit x tends to c, f of x is equals to f of c. If this holds, then we say the function is continuous at that point. Now, what about the endpoints? What about this endpoints, this a and b? When we say that the function is continuous at a and b in this closed interval a b, let us define as, let's for x equals to say a, then we say f is continuous at x equals to a if it's like, see, this is our close interval ab, so only possible way to close a is if we come from the right hand side. So what should be the intuition? That its right hand limit should be equal to its function value. That means is said to be continuous if its right hand limit, that is limit of x tends to a positive f of x, like forgot about the elements outside this close AB. So what we have the elements only inside this AB close AB. So to if we have to like take the limit, so we have to take only our right hand limit. So that means our function f is said to be continuous at x equals to a if our right hand limit is equals to the function value. Similarly, at x equals to b, we say f is continuous at x equals to b if our left hand, because only possibility to come close to b is from the left hand side, so it should be like it's the proper intuition that our left hand limit of b should be equals to its function value. So what we have concluded that our function f is said to be continuous in closed interval a comma b when every point in this closed interval a comma b is continuous. F is continuous at every point in closed interval a comma b. Okay. Now, if I will tell you the graphical intuition, okay, first we will do the algebra of continuity, then we will see the graphical intuition of continuity. Okay, now what is algebra of continuity? Like it's very important for us if we know the continuity algebra of continuity, because if we know it, then we can find easily. If we know some continuity at some particular function, then we can find on another function also. Suppose f of f and g be two functions and they are continuous at say x equals to a, then then following holds. That is first one, f plus g and f minus g is continuous at x equals to a. Second, that is about scalar multiplication, that is c times of f, that where c is some real number, is continuous at x equals to a, where our c is some real number. Then third one is the multiplication, that is f dot f multiply with g, that it is defined as, if I will try to define it, is f dot g of x. It is not composition, it's just multiplication of function. It is defined as f of x dot g of x. Now, if f and g both are continuous at a, then f multi g is also continuous at x equals to a. Now, last one, that is f divided by g. If f and g is continuous and f of a is not equals to 0, then we say that f quotient g is continuous at x equals to a. This is algebra of continuity. If I will try to say its use, take an example, say 1 plus x. We can easily see that 1 is a constant function. It will be continuous. X will be continuous. We have already find it earlier. Then we will say, take my, if I try to explain you by graph, take f of x as 1 and g of x as x. So our f of x function is this, right? This is x, this is y, this is my f of x function. Okay. So as you can see, at x equals to 0, it is function is continuous because it's take the value 1 and the function value, like limiting value, is also 1 and its function value is also 1. So it is continuous. F of x is continuous at x equals to 0. Now about g of x. Our g of x is defined like this. It is our f of x and this is our g of x. So our g of x is defined like this. So this is x and y. Okay, as you can see by graphically, its limiting value at 0 is 0 and the function value is also 0. So what we get, that g is also continuous at x equals to 0. Since by using the algebra, we can easily say that f plus g is continuous at x equals to 0. So what we get, our 1 plus x is continuous at x equals to 0. Now, what we do is, let's do some geometric interpretation of continuity. Okay, so what is the geometric interpretation? If I will change my pen as it is important. So what is geometric interpretation of continuity? It says that if you can make your graph without lifting your pen, then your function is continuous. If I will give you example, take example, as you can see, our first example, that is f of x. F of x is x. Its graph is like this. As you can see, you can make your graph without lifting. So, as in this example, we have make our graph without lifting our pen. See, this is our graph. We didn't lift our. Okay, my mistake. I just made multiple lines. Okay, so so as we can see, we make our graph without lifting our pen. So what we can see, that our f of x equals to x function is a continuous function. So it's in graphical way, graphical approach to see whether the function is continuous or not. And it's always a very good way to see by this way. Now let's do some remark of continuity. Okay, remarks Okay, first one is very important, that is every polynomial function are continuous in their given domain. That means you know that polynomial functions are of the form, say, like an x raised to n plus an minus 1 x raised to n minus 1 plus up to a0. So this step, our polynomial functions are always continuous in their respective domain, the domain which we have selected. Then the second one, it is a standard continuous function that is always continuous, which you guys should always like remember, that is f of x is mod x. It's a standard continuous function, and you will see it's important in differentiability also. See, its graph is given by this, right? This is 0 point, and this is our x-axis, this is our y-axis. Our y is nothing but y equals to f of x, and our f of x is nothing but mod x. So it is a continuous function. As you can see, we make our graph without lifting our pen. So what we can say is that this graph is a continuous function. And another, what you guys can think to remember, like these two are the standard one. Yeah, like you should always remember these functions, that they are continuous functions. Now let's move ahead to the next topic, that is differentiability. Now differentiability is one step ahead from the continuity, like its definition. Now fine, let's its definition. Differentiability of a function f, which is a real valued function, say x is a subset of R, to R real valued function. Differentiability of a function f at a point, say x equals to c, and it is given by, we say that f is differentiable at a point x equals to c if the limit h tends to 0, f of c plus h minus f of c divided by h exists. If this limit exists, then we say that our function is differentiable at x equals to If it holds, like if it exists, then we say our f is differentiable at x equals to c. Now we can see that it's another way to write, that will be limit in terms of c, that is limit x tends to c, f of x minus f of c divided by x minus c. That means if this exists, this both limits are same. If this exists, then we say our function is differentiable. As you can see, this will look like rate of change. Okay. If you can see, I will just explain you by diagram. Say this is some function. This is our x equals to c. So this is some point. So what we are doing, that we are taking the point this and this. This is what is this point? This is our f of like c plus h something point. Then sorry, this is our here. This is the image. So what is our like domain here? That is c plus h, and and this one, this is our c comma f of c. So this is this line. So we have this line as in this limit. So as we come closer to closer, and we are also taking from the left hand limit, so this is this point. As we come closer and closer, this will become our tangent line. I change my pen so it will be more clear to you. So this will be, if we come closer and closer, like closer and closer, if we reduce the size of h, then we come to this point, and then this line will become this line, which will be the tangent. So what we can say, that the differentiability of a function at a point is nothing but rate of change of that function at that particular point. Okay. Now how it is denoted? Its denotation is say f dash of c, or we another way is d by dx, like we are differentiating with respect to x, It is dy dx of f of x at x equals to c. Then if this limit exists, then we say then the function is differentiable, and the differentiation of this function at c is denoted by f dash of c. Now let me do its algebra of derivative. Now it's very important, the algebra of derivative, because it will help us to find the like differentiation of some other functions by using the differentiation of some known function. Now let's say u and v are some functions, then such that they are differentiable, such that they are differentiable. Need see, this is important condition, that they should be differentiable, that they are differentiable at, say, we are talking about differentiability at a point. So then first one is differentiation of their summation, or like addition, or like subtraction. So it's different. We know that their differentiation is denoted by dash. The dash represents the differentiation of a function. So it is given by u plus minus of v dash, that is u plus v whole dash, that is differentiation of u plus v is nothing but u dash plus v dash, that is differentiation of u and differentiation plus differentiation of v. Then the second one is the product, differentiation of the product, that is differentiation of u dot v, which is given by u dash v plus u v dash. This is called product rule. Then another one is the differentiation of their difference derivative, like dividend, or quotient, that is differentiation of u by v. We're given that our v is not equals to 0 at that point. Okay, so u by v dash whole dash is given by u dash v minus u v dash divided by u square, sorry, v square. So this is our algebra of differentiation. Now by using that, we have some standard differentiation, that or standard derivatives. Standard derivatives, which you guys should know. That first one is derivative of x raised to n. It is given by n times of x raised to n minus 1. Then second one is derivative of sin x. We know that sin x derivative is, they are standard derivatives, so you should like learn this formulas. That is sin x whole dash is cos x. Then third one is cos x whole dash, that is derivative of cos x. This is nothing but minus sin x. Then last one is 10, which is easy quite by you, because you can easily find from this, that is derivative of 10x, which is nothing but sec square x. Okay. Now let's move to the world of derivative. It's very important, like derivative plays a very important role. But before that, let's look at the relation between the differentiability and continuity. Okay. See, okay. So first, there is a remark for you, that you should like remember this, that or I will explain you the reason also. The first is, if our function f is differentiable at x point, say x equals to a, then this implies f is also continuous at x equals to a. That means differentiability, in short, you can learn it by DC, that is differentiability implies continuity. Okay, but the converse is not true, right? But converse is not true. I will give you one example also. Before that, like see how this is coming. It's like normal proof, you can say. It's okay. Let me explain you the proof also. So suppose we have to check the. We are given that f is differentiable at x equals to c. Then our f of x minus f of c can be written as f of x minus f of c divided by x minus c multiplied by x minus c. Now take the limit x tends to c. So this will be f of x minus f of c is equals to limit of x tends to c, f of x minus f of c divided by x minus c. We know that this limit will exist because the function is differentiable. So this is nothing but derivative of the function if I give the limit to this, and we know that this limit is 0. So what we get? This side will be 0 and this side will be limit of x tends to c of f of x minus as there is no x, so its limiting value of f of c is nothing but singleton f of c. So what we get? The limit from here, what we get? Limit of x tends to c f of x is equals to our f of c. So what we get? We get the limiting value and function value are same. So from here, what we get? F is continuous at x equals to c. So what we get? The relation that if the function is differentiable, then our function is also continuous. Now, before moving the converse, let me explain you the geometric interpretation of differentiability. That is, let's give the new heading, that is geometric interpretation of differentiability at a point say x equals to a. So what is the geometric interpretation? We know that the differentiability at a point is related with the rate of change. So what we say, our f is its geometric interpretation is that f is differentiable at I just write it in short form, that is DIFF for the differentiation. F is differentiable at x equals to a if it make a unique tangent there, tangent at x equals to a. So for example, take the graph. This is f of x equals to x square. As you can see, let's check the differentiability at x equals to 0. As x equals to 0, as you can see, there is only one unique tangent. This is x equals to 0. Sorry, y equals to 0 axis. That is, or sorry, y equals to 0. That is nothing but our axis. This is the only unit tangent. Now take the example as mod x. We know that f of x equals to mod x. As you can see, our mod x graph is continuous because we can make our graph without lifting our pen. That is, we see, I didn't lift my pen to make this. So this is our y, this is our x, and this is y is equals to mod x. As you can see, our function is continuous at x equals to 0 because it is continuous in its whole domain. But as you can see, in at x equals to 0, we can make different tangents. Say, take this one, this is our one tangent, this is our another tangent, this is our third tangent. So what we can say, at x equals to 0, tangent is not unique. Since if tangent is not unique, tangent is not unique. If my tangent is not unique, this implies our f is not differentiable at x equals to 0. So what we get? That the function is continuous, but it is not, a function is continuous at 0, but it is not differentiable at 0. So we also get the counter for this statement that the converse is not true. So what we get? Our mod x, this is an important statement for you, that mod x is continuous at x equals to 0, but not differentiable at x equals to 0. So what we get? That the continuity does not imply differentiability. Only differentiability implies continuity. That means the DC current is allowed for to learn like trick for you guys to learn. That is DC. That means differentiability implies continuity. DC is a current. Then DC implies, that is the differentiability implies continuity. But the converse is not true. That means continuity does not implies differentiability. Now, let's move ahead to the world of differentiation. For that, we have to find the differentiation of different functions. So, first, let's suppose if you guys have a function of the form, say, f of x. is equals to, let me change my pen with black color. If you guys have a function f of x equals to say 2x plus 1 whole square, then we don't like, it's easy. We can find its derivative at any point by using the limit. But as you can see, we can convert it in another form. Like if I divide it in two parts, two different like functions, then where we know, as we know that we know its derivative 2x plus 1 derivative, and we know t square derivative. Okay, if I write f in like a composition of two different function, and then I find the like differentiation of this two functions, then combine them to find the differentiation of my f of x, then it will be easy for us. Like going by definition is also good, but if I have a trick to find the differentiability without going to that limit, then it's also fine. So this is nothing from here. It's come derivative of a composite function. For that, we have, in another word, we have a chain rule. Suppose my function f of x is of the form composition, that is v composition of u, that is v composite u function. Okay, so to find its like a derivative, mean this by say, okay, if we have to find the derivative of f with respect to, okay, here our, see, whenever we find whenever we find our derivative, we always find with respect to independent variable. That means what is independent variable here? So say if my y is completely written in terms of x function, then what we say, that y is completely dependent on x. So here our x function, sorry, x variable is a dependent independent variable, and y is the dependent variable. So if we have to find the derivative, so here what we find, that the derivative of f with respect to x, that is df by dx, so it will be given by chain rule. It will be given by, so before that you take the chair, like convert it in different formula, then you only use the chain rule. So what we use is, take name our u of x as t. So our v of u of x will be nothing but v of t. So what we will do, we will differentiate v with respect to t, and our u with respect to x. So what we get, df by dx can be given by derivative of v with respect to t, and derivative of u, which is nothing but t, that is dt, with respect to x, that is dt by dx. Okay, this is a chain rule. This is nothing but a chain rule. That means you are finding the derivative of the required function using a chain, that is dv by dt multi dt by dx. As like it's easy to learn that how you come that this should come, because like after cancelling this you get your required one. Okay, now let me explain you, like it's like the theory is quite difficult you for understand. Let's do it by example, then you will like understand it properly. So take our the one which from by which we like started this topic, that is our, take our f of x as 2x plus 1 whole square. Okay, take our ux as 2x plus 1, and our v t equals to t square. So if I differentiate u with respect to x, we can easily differentiate by using like our standard form differentiations. Okay, and so, and if I try to differentiate v with respect to t, this is also easy. We know that if I differentiate v with respect to t, this will be nothing but 2t. And if I differentiate u with respect to x, this will be nothing but 2. This is just the derivative of 1, because the derivative of a constant, you can easily find that the derivative of constant is always 1, and derivative of 2x will be 2 into derivative of x, and we know that derivative of x is 1. So derivative of u by x is 2. Now what we have to find? We have to find the derivative of 2x plus 1 whole square. That means we have to find df by dx. Now apply our chain rule. For chain rule, I just wrote my f of x as a composition of V composition u of x. That means V of u of x. So like it's easy that it is true, right? Because what we have taken, our u of x is nothing but 2x plus 1. Now for v of t is nothing but taking its square, that is nothing but 2x plus 1 whole square. So it's true. We have taken our f, like it's fine that the composition we have taken is true. Now by chain rule, what we will do? So df by dx will be given by dv, differentiate v with respect to t, and differentiate our u, which is nothing but our t. Take it as t. So differentiate u, that is nothing but our t, that is dt, with respect to x. So we know that our dv by dt is nothing but our dv. Take it as, if you take it as t, then differentiating t with respect to x will be nothing but 2. So what we get? Our dv by dt will be 2t, and our dt by dx will be 2. Just put the values. So what is our value? So what will be our value? Our value will be t is nothing but 2x plus 1 multi 2. So its derivative will be 4 times of 2x plus 1. So our df by dx is, like we can easily find using definition also, but like definition is not always good to find our solution by definition, because it will be lengthy. So we have this trick. So this trick is for finding the derivative. Like if we convert our function as in a composition, then we can directly use our chain rule to find the derivatives. Okay, now let's move ahead. The another one is derivative of an implicit function. For that, let's before learn what is implicit function. Implicit function, we know that if my function f of x, say we name this by y, like we name by we write our y in terms of f completely, then this function is called explicit function. If my y is completely written in terms of x, then it is an explicit function. But suppose if it is not, then such function are called explicit function. So let me tell you some examples. So take an example. Take say y plus sine y is equals to x. See, you cannot write your y completely in terms of x, because if you try, you cannot write it. So what we say, that our this function, this y function, y equals to f of x function, y cannot be written as f of x. So this function is our explicit function. Okay, now if we have to find its derivative, like if we have to find dy by dx, then now if we have to find the derivative of this explicit function, so for that what we have to find? We have to find dy by dx. So what we have our function as in the form y plus sine y is equals to x. So what we can do, differentiate both sides with respect to x. So what we get? Our dy by dx plus d by dx of sine y is equals to d of derivative of x with respect to x, where we know that this derivative will be 1. Like we can easily use the standard form that I told you, that x raised to n derivative is nothing but n multi derivative of x raised to n is n multi x raised to n minus 1. By using that, its derivative is 1. So what we get? Our dy by dx plus, by using chain rule here. For chain rule, what we get? It is a composition of sine and y function. So what, by using chain rule, what we get? Derivative of sine, differentiating sine y with respect to y, then differentiating dy by dx is just a chain rule. Then derivative of dy by dx is nothing but 1. So by this, what we get? Our dy by dx, derivative of sine y, we know that a bystander, that is derivative of sine is nothing but cos y. and dot dy by dx, this will be 1. So from here what we get, our dy by dx will be nothing but 1 upon, this will be nothing but 1 upon 1 plus cos y. Okay, observe that our cos here, our y cannot be, here our y cannot be, like when our cos is minus 1, that is cannot be 2n plus 1 pi. Y cannot be this, because if it is 7 then the function is not defined. So y is not this, other than y values are allowed. So what we get, to find the derivative of explicit function, we just try to like differentiate both sides with respect to x, then use our chain rule or standard form, then it's become quite easy to find its derivative. Okay, now let's move ahead. For this, now we have what we have, differential derivative of an inverse trigonometric function. Okay, for inverse trigonometric function, like it's enough for you guys that to learn their formulas, because its proof is quite lengthy. It's not needed for you. So just learn their formula. So I will tell you some standard one. They are enough for you to understand. So what is the derivative of sine inverse of x? Its derivative. So its derivative is nothing but 1 upon root of 1 minus of x square. See here our x is not equals to plus minus of 1. Okay. The second one is derivative of cos inverse of x. It is nothing but same as sine, just change the sign, that is minus of root of 1 minus of x square, where our x is not equals to plus minus of 1. Okay, now last one, that is like these threes are important only, that if you know this then you can easily find the others also. That is tan inverse of x derivative, which is nothing but 1 upon 1 plus x square. Okay, they are the required derivative of an inverse function. Now let's move ahead for, okay, now we have some important, they are the important derivatives. Like you guys will notice in your future also, when you go for higher studies, then the derivative of the exponential and the logarithmic functions are very important. For first we will introduce what is our exponential function and what will be our logarithmic function. For exponential function, if my base is let my base, for exponential function we always need a base b, which is always a positive or must be greater than 1. Then my function f of x defined as b raised to x is called exponential function with with base b. Okay, see its domain is whole R, and if you make try to find its graph, you will also find that its range is also whole, sorry, not whole R, it will take only positive values, that is positive R only, that is R positive, union 0 also, because no, 0 will not come. Okay, in exponential 0 will not come. Okay, so its range is only positive R, its range will be only positive R. Like it will take the 0 value at the limiting case, so which is kind of not defined thing. Okay, now the another function, this is our first function, that is exponential function. Exponential function is type of b raised to x. This is called an exponential function, where our base b is called the base and it is always positive. Then the logarithmic function. Logarithmic function, its domain is always positive. Like logarithmic comes from the exponential only. Then it is defined as it is a function from a positive r to whole r, and it is defined as our x maps to log with base b of x. Say if it is y, then this is defined as this. If my p raised to y is x, that means what we are saying, that my x maps to log b of x. If this will happen if my b raised to y is x. So what you can see, that the log function is just, this is look like by my exponential function, like this is exponential of like f of y. F of y is equals to b raised to y. So what we can say that my log function is just comes from my exponential function. So our log function is defined like this. So before that, let's move ahead. Is I will see if there is some another point to tell you. Like you can think. Yeah, it's fine. If you want to see their graph also, so your log exponential graph is of the form this type. At 0, it will take value 1, then it is kind of this form. Okay, it's like increase explicitly, like with very high speed. Okay, then by log, my log function is defined as at 1, it will take value 0. So it is defined like this. This is its graph is like this. I just need to not at all good at graphs, but let me try once. Then its graph is log x graph is at 1 it will take value 0, that it is 1 comma 0, and its graph will go like this. Okay, this is my exponential graph and this is my logarithmic graph. Now let's move away ahead. Now, very important part is properties of loss function. This will help you a lot in like solving some differentiability or continuity as well. So first one, if you have to change your base, that means as you can see, this is nothing but base of the log. This is nothing but the base of your exponential. If you have to change your base in log, that is so. Right now, suppose you have a base a log with base a of p. This can be written as log with base b of p divided by log with base b of e. So this is like to change your base, change base. Now another one. The second one is log of p multi q. This is nothing but log of with base a of p plus log with base a of q. This is just you can say product form or product form, yeah, or you say product rule. Then third one, only this part is important. Like you will come across many times for this formula because this is a very important. I will tell you as an star point. This is very important. Like next two will comes from this also. So log with base a. If you have p raised to n, you can write p raised to n as p multiply n times. So this can be written as n times of log with base a of p. Now, fourth one is division. That is log with base a of p by q. This can be written as log with base a of p minus log with base a of q. These are the like important algebra. You can say algebra of logs also, but they are the very important properties of log. Now let's move ahead. Now the logarithmic differentiation. Now suppose if you have your function y of the form say u of x to the some power, say v of x, then how to find its derivative? So what we can do, we can use our log property here. So if I apply log both sides, then its power will come like its power will come out. So we will use this. Take log both sides. So what we get? Say take natural log. If you have e, that means log e means natural log. Okay. So natural log of e of y, take just log both sides. So this will be log with base e of u of x whole raised to v of x. This can be written as take our v outside, that is v of x log with base e of ux. So this is our log with base e of y. Now differentiate both sides. Now just use our chain rule or whatever we know about our derivatives. So differentiate with both sides. So for this, what we need. Okay, before that, maybe I should tell you the standard logs, that is, sorry, standard derivative. So first one is differentiation of our exponential function, that is e raised to x function. This is nothing but e raised to x. This is our first one. Just remember this, because its derivative is not in your 12th class also. 12th class also, it will come in higher studies. So derivative of e raised to x is nothing but e raised to s. Then the second one, our derivative of log with base e of x is nothing but 1 by x. This will also come in the higher studies. That so what from here what we get? The derivative of exponential is nothing but exponential itself, that is e raised to x, and the derivative of log ex, e is just representing a base e, which is like it's an like notation. It's a notation, just like it's also take a value, but its value is not a fixed quantity. It's just non-terminating. That's why we name it by e. So if we have to differentiate with e raised to x, then it is e raised to x. Now differentiation of log x. Log x differentiation is 1 upon x. Now let's move ahead. So if what we are doing here, okay. Now what we are doing here is differentiating. Now differentiate both sides with respect to x. Sorry, with respect to x. So by using chain rule, what we get? That like just differentiate both side with respect to x with v of, now here we will use our product rule also. So here, so in left hand side what we will use our chain rule, that is log derivative of differentiation of log y. This will be nothing but 1 upon y. Then differentiate our y, that with respect to x is nothing but dy by dx. Then the next this side first use our product rule, that is v dash of x multi log e of ux plus vx multi derivative of log e of ux. So if we will find this, then this will be 1 upon y dy by dx. This will be v dash of x log e of ux plus v of x. Now differentiate by using chain rule. So with chain rule, we will first differentiate log u, just differentiate log ux. Then this will be with respect to u itself. Then this will be 1 upon ux. Then the derivative of ux with respect to x, this will be ux dash. So what we get? Our dy by dx will be nothing but y multi v dash log e of u plus v upon u dot u dash. So what we get? If I have like if we have the logarithmic like if we have to find the derivative of the form ux raised to vx, then its derivative, that is dy by dx, is given by y multi v dash log e of u plus v by u dot u dash. So let's check if we will try to find some others. So, for example, hmm, okay, so I will give you example here. Take an example. It's like it seems difficult when you see theory, but if you use your theory in the examples, then it will be very simple for you. For example, say I will take my y as a raised to x. Okay, so then we can say its derivative, that is y dash, can be given by a raised to x, that is y multi v dash, here our v. So here our u is nothing but a and our v is nothing but x. Just put the put use this formula. Just use this formula, that is a raised to x. Then our v dash, this is 1. Then log of u, that is log of a with base e. This is all natural, that it is natural log. Then plus, then it will be plus of u v by u. Our v is nothing but x and our u is nothing but a. Then the derivative of u. That means derivative. U derivative of a. That means a dash. We know that the derivative of constant is 0. So what we get? Our y dash is nothing but a raised to x natural log of a. So what we did? just apply our logarithmic differentiation here. So like it's easy to find the differentiation if your function is of the form say u of x to the power b of x, then use this logarithmic differentiation formula. Now our last topic. This is a derivative of function of a parametric form. First of all, we see what is parametric form. What do you mean by parametric form? Parametric form. Suppose you have your function x and y completely in terms of third variable, that is third party we say, or say third variable, then we say that our x and y functions are parametric, are in their parametric form. Suppose if I tell you by example that my example is say if my x is some f of t and my y is if my y is some g of t. As you can see, my x and y are completely in terms of a third variable, then it is said to be a parametric form of x and y. Then now if we have to find the derivative, that is dy by dx, then how we can find? So for that we have a derivative or derivative of a function of a parametric form. So for that what we do, to find our dy by dx, we will use a chain rule. So for chain rule, we differentiate our y with respect to t, differentiate our y with respect to t, then differentiate, sorry, by mistake, I should first try to explain the derivative of y with respect to t. So for that, okay, now let's do it again. Okay, so since our y is completely in terms of t, so our dy by dt, if I use my chain rule, then it will be y with respect to x. Suppose my y function is in terms of x, so our dy by dx, if I use my chain rule, then dy by dx dot dx by dt. Then from here, what we get? Our dy by dx, this is just chain rule, this is chain rule. And now we are finding our required dy by dx. This will be nothing but dy by dt divided by dx by dt. If I will give you a hint, how should you guys learn it to find the derivative of a like parametric form? Just to find dy by dt, what you do is differentiate your upper with respect to t, because you have y in terms of t. Differentiate your lower with respect to t only. Then as you can see, this and this, like it's just to hint to how to remember. It's not like this, but see, your this part and this part will come, then you will left with your dy by dx. So what you have to do is differentiate your upper one with respect to the t, like the third variable, differentiate your lower one with respect to t, then you will get your dy by dx. Now let me explain you with respect to with some example. Take an example. Suppose your x is some a cos theta and your y is say a sin theta. Then if you have to find, now you have to find your dy by dx. How can you find it? So as you can see, x is completely in terms of theta, y is completely in terms of theta, so they are in their parametric form. Then we can easily find dx by d theta, because we know that the derivative of cos is nothing but sine minus sine, that is minus a sine theta. Then our dy by d theta will be a cos theta. So now what will be our dy by dx? Just put this formula. So by this what we get? This will be dy by d theta divided by dx by d theta. So this will be a cos theta divided by minus a sin theta. So this will nothing but our cot theta. So what we get? Our dy by dx will nothing but cot theta. So now we also find the derivative of the parametric form. Now what we have find, like we just completed all our topics. So this is about continuity and differentiability. Now we will continue with the questions in the next videos.